Good afternoon, everybody. Thank you for being here this afternoon. I say afternoon because this is from Singapore. So what you see on the screen is we are the Royal Aeronautical Society Singapore branch. You see there is in the middle the logo, but we also have two logos here because we also represent the student chapter at Singapore Institute of Technology and University of Glasgow, because the reason is because we organize this lecture or webinar for our students in the joint program between University of Glasgow and Singapore Institute of Technology, or SIT, for the aerospace engineering program. So we also open this to the community of the Royal Aeronautical Society, especially for Singapore and everybody around the country. But we know that we have people joining from the UK and other parts, India, if I'm not mistaken. So we are very happy to welcome everybody. The topic that we're going to hear today from the speaker is, I think, concerns us or everybody who is interested in aerospace. Before I start, I just want to say that we have here Dr. Ian Taylor, Head of Discipline in Aerospace Engineering from Glasgow University. And we also have Henrik Hesse, who is Program Director from Glasgow in Singapore. So I'm going to also ask if Albin, who is our chairman of the Singapore branch and student chapter, can share with us who they are.
Right. Okay. Hi. My name is Albin. Good morning to those from the UK and good afternoon for my fellow classmates. Again, my name is Albin Chua. I'm the chairman of the RAeS Singapore Branch and the SIT student chapter. I would like to take this opportunity to briefly share on who we are and what we do. So a brief history on RAeS. It stands for the Royal Aeronautical Society, and it was first founded in 1866. And the objective of the RAeS is to contribute to the advancement in the field of aerial navigation and in aerology. Just a fun fact that RAeS set up a technical department during the war times in 1940 to expand the aircraft industry, mainly to bring together the best available knowledge and present it to as an authoritative and accessible format. They provide working tools for engineers who might come from other industries and the lack of specialized knowledge required for aircraft design. This technical department became a separate entity, which is now known as the Engineering Sciences Data Unit, or most of us know as ESDU. So it's based in London, and RAeS has over 22,000 members worldwide. Inculcating the same ideologies, the Singapore branch and SIT UOG student chapter was first inaugurated in December 2020. The committee is currently student-led under the guidance of Dr. Arturo and Dr. Henrik, who's in this call now. They are also our academic professors as well. Our goal is to provide our members the avenue to develop themselves through their interest in aerospace. We have over 30 students from different courses such as aerospace engineering, mechanical engineering, aerospace systems, and air transport management. Shown on the screen is the organization chart of RAeS. Yes, the academic liaison officer is Dr. Arturo. It has been revised through the time we have been expanding. The branches on the right and on the bottom falls under the Singapore branch, where our main focus is to constantly liaise with external industries to create opportunities for our members. The branches on the left falls under the student chapter, where our student members from various courses get to communicate with one another and learn, and hopefully to learn from one another through their shared knowledge. So these are just some of the faces of my dedicated committee, and I'm happy to share with you that we have recently recruited 2 junior members, Ashley and Hakim, who came forward to express their interest to serve the student chapter committee. So some of the events that we had opportunity to plan was the Aspire Aeronautical Challenge, which was created by New Aeronautics and Urban Air Mobility Company. They encourage students to create innovative ideas in the field of aviation, and if their ideas stood out, participants' project will be funded and developed, will have a chance to develop it further and possibly commercialize it. We also had the opportunity to join D1 Racing, a drone racing organization that wants to promote this sport in Singapore and ask students from SIT to participate in the event. Our team also participated in an online competition called AeroTube, where the focus was to share anything related to aerospace. Future of Transportation is the title of our video project, which well informs the audience of the possible mode of transport in the future, such as air taxis and VTOL options, as well as the challenges and limitations of having these modes of transport in the current times. Some of the events that we are planning to do next are the Y Aviation Conference, together with many aero societies from Nanyang Technological University, Singapore University of Technological Design, Temasek Poly, and many more. The conference aims to share the importance of innovations through sustainable air travel and greener airports. You can learn more of the event details by searching Y Aviation in LinkedIn, and if you have the time, please come and join for the conference. Another event we are also planning is to have a joint webinar with Singapore Institute of Aerospace Engineers, so do look up for that too. So I will not take so much time of your time. I have ended my sharing. I will thank all of you for your kind attention. I will now hand the time back to Dr. Arturo. Thank you.
To the main matter that why we are here is because today we are pleased to welcome Dr. Albert Van Gerden, a very special guest from Cranfield University in the UK. Dr. Van Gerden is better known as Esteban, and Esteban is a research fellow in the Center for Propulsion Engineering and Rolls-Royce University Technology Center at Cranfield University. His research is unified under three themes. He works on conceptual aerospace vehicle design, the study of advanced airframe and propulsion systems, and the technical and economical assessment of novel aerospace technologies at vehicle level. So Esteban has a PhD in aerospace engineering from Cranfield University, a master's in science in aeronautics from Caltech in the USA, and a BH in mechanical engineering from University of Pretoria. So if you're wondering where is he from, he's South African. And today he will be sharing with us his expert opinion on how industry and academia are trying to articulate the challenges posed by infusing evolvability into aircraft design. The title of his presentation, as you can see on the slide, is Darwinian Airplanes Evolving to a Future of Sustainable Aviation. So with that, I ask you to give your full attention to Dr. Esteban, and help me to welcome him to the virtual stage or screen.
It's a privilege to present this topic to you. It is a topic that is very ubiquitous in aerospace, but not well understood and not something you can find easily in the literature. So this is all about evolving aeroplanes. Thank you very much, Arturo, for the introduction. I hope that you'll enjoy this little presentation I've prepared for you. So the talk will follow a very sort of educational bent. Because this is mostly for students, I'm going to explain what evolvability is, how we define it, and then how we try to design for it. However, at the end, I will talk a bit about some of the challenges for the future, which I'm leaving to you guys to solve. So I'm going to give a brief introduction. I'll give some examples of changeability. Changeability is a related topic, which is very important to define to understand what evolvability is. I'm then going to define what evolvability is, and then explain how to design for evolvability, or how we try to design for evolvability. I'll give a brief overview of my own work on evolvability, and then discuss the challenges and opportunities for the future. So what I have here is some images of very, very nice, well-known historical aeroplanes. What we've got there at the left is an aeroplane that many of you would think would be the 707, but that's actually the Boeing 367-80, which is the ancestor of the 707. We've got the Boeing 747 there in the center, top center. On the right-hand side there in the top, we've got the Concorde. Then we've got the Airbus A300. There in the bottom left, the 787 and the A380. And what all these aircraft have in common is that they were they represented the beginning of a new era, and they represented the vision of the companies for what the future should be. There was an incredible risk with each of these, developing each of these, extreme uncertainty, very high investment required, and that means that if you're going to invest that much, you have to be really sure about what you're doing, and your aircraft you would want to be evolving very far into the future. So you would want it to be applicable very far in the future. So with that, we get some idea about what we want from a design, that we want to reuse it as far as we can into the future. So evolvability is something called an ility, what more formally known as a life cycle property, or sometimes we just say X, so if you design for X. Now, life cycle properties I'll explain by using a very simple example. So if you have like a little scooter you want to buy, you'd be interested in you know, how well it will work, and how fast it will go, maybe if you want to race with your friends, for example. So you'd be interested in that. But more likely that your decision will be influenced mainly by a few other things. How durable it is, how safe it will be, how maintainable it would be, what the quality will be, and these things. So these are things we call life cycle properties. So it's not directly related to the performance. It's something else that we want. And it's quite difficult to define and difficult to design for. And designing for these things often increase cost and development time. A particular type of ilities which is applicable to this lecture is change type ilities. So ilities that have to do with change, and there are many of them. We've got flexibility, versatility, evolvability, adaptability, and so forth. Robustness is also an ility, a change type ility. We collectively refer to these as changeability. There's a lot of confusion in the academic literature on these terms, and people use it differently. Some make their own definitions, and sometimes they don't. It seems like we've got these research islands where authors don't know what other authors are doing on the same topic. So we could even have a fancy term like change adaptive flexibility to get a common term. But changeability is the term most often used as a collective term for all the ilities. I'm going to give a few examples of changeability now, so of the different types of changeability we can see. So I'm going to do a little poll here. Now, what we've got here is the Douglas DC-3, which is an aeroplane that has not changed a lot, but has been in service with many operators for decades. It's a very reliable, well-built design, and it just is a workhorse that continues working. So what would you, the world is changing around this aeroplane. Technology has improved, everything else, but still we use it. So what word would you use? And this is a question now for the audience, for all the students. So Ashura will put a little poll. What word would you use to describe this ability to handle change? So shall we say it's robust or adaptable or flexible? I can see the numbers.
Adaptable, it looks like the preferable one.
All right. Well, you're all wrong. It's actually all of those terms. You can call it whatever you want. So you're actually all correct. I should put it rather that way. A term we often use for this where the aeroplane itself doesn't change or doesn't change much, we call it robust. It just absorbs changes as it goes on without being changed. There are very few examples of aircraft that or system engineering systems like this that that just don't need to be changed, and this is simply because you don't want something amazing from it. It's a well-designed, it's almost an over-designed airplane that just simply does what it does, which is to transport things. I'm going to go to a next changeability example. Can't move on to the next slide. So I'm going to use the word flexibility a lot, flexibility and adaptability, just because, as I said, these words, essentially you can use whatever words you want. Some words just naturally seem to fit better, to fit the examples better than others. So for example, you guys all chose adaptability. I would also probably have called it adaptable. It's just in the literature we often refer to that as robust, but again, it wouldn't be consistent. But flexibility, most authors use when a change is made onto the system. So from outside the system boundary, you make a change to the system. Whereas adaptability is more when the system changes itself. And robust is just, it doesn't need to change. We've got other things like versatility and reconfigurability. Now, reconfigurability, a very common example would be military aeroplanes, where we've got the ability to attach different types of weapons to the aircraft for it to perform different roles. Now, that's versatile, or you can call it reconfigurable. You can also say that an aircraft that can fly very far is versatile, just because it can cover many routes. Now, where this often goes wrong is when an airframer tries to introduce a short-range version of an aircraft. The philosophy is always that it would fly these short routes more efficient. And most routes, the overall majority of routes operated by airlines are shorter routes. So the philosophy would be, okay, why not just optimize an aircraft route? The problem is that airlines have a mixture of routes, and they want to use their aircraft both on the long routes and short routes. So these short-range aircraft, every now and again you see one introduced, but they don't perform very well. Sorry, I should point out it's the image here at the bottom right, the 787-3, which never made it to market. The 787-8, which you see in the top, obviously is a very successful aircraft that's got a very long range. Okay, another type of ability is reconfigurability. Again, in this case, it's more that the airplane changes itself, or the system changes itself, if you consider the pilot to be part of the system, where you could select a different type of geometry. Most of the cases, these are automatic, these changes in geometry. So we've got the swept wing B-1B Lancer bomber here on the right, and the V-22 Osprey here on the left. So these aircraft change their geometry, the wing with the B-1B bomber and the angle of the propulsors in the V-22 Osprey. They change themselves to adapt to the different conditions of the mission, or to perform different parts of the mission. Now, I often wouldn't consider this a life cycle property because this has to do with the performance of the aircraft. It's something that's separate. So for me, a life cycle property is usually something that has to do about what happens between missions. But many authors do consider that a life cycle property. Another one is customizability and versatility. Now, this is a very, very common one. This is the concept of aircraft families. So it's not the aircraft itself or the design itself that could be changeable. It could be a whole product set that together is customizable or versatile. So we call these product families or product platforms. So the example here on the left is the F-35 Joint Strike Fighter. So this aircraft has been designed for the US Air Force, Navy, and Royal US Marines. And the aircraft of the three variants share many common parts and so forth, many common systems, but there are significant differences as well. And this allows the Air Force or the services to keep maintenance costs, acquisition costs low, but to do these different types of missions or to meet the different requirements of the forces. A very common one on the airliner side is to what we call stretch the fuselage. So you put in plugs, what they call plugs, to lengthen the fuselage. That's a very common example of increasing payload, often at the expense of range, but not necessarily. And I'll go into a bit more detail with that. Upgradability. So a good example is the B-52 bomber. This is again an aircraft that's been in service for a very long time, since the early 50s. And it has seen extensive upgrades, not on propulsion-wise, which is interesting, but on systems, the types of missions it can carry out, and the types of weapons it can carry out. And again, this is a good example because it's a good example of over-design. The wing here you can see is enormous, very high aspect ratio, very low wing loading, so very large wing that allows all these changes to make. So you've got a lot of space and extra weight that you can carry, so you can make these changes. Now I'm going to do another poll. So if we've got pictures like this, so we've got the F-18 there, different variants of the F-18, and there's an element of time, and we've got different variants of the Boeing 737 there. And I've got my little picture there. So what word would you use to describe this ability to handle change? And now this is a trick question. Is it adaptable? Is it versatile or evolvable? Okay, it's a spread pretty even. Okay, I shouldn't have said it's a trick question. I made it a trick question by saying it's a trick question. This is what we really refer to as evolvability, and the distinguishing factor is that there's this element of time and the design that changes over time. And I'm going to go into a bit more detail on how we recognize what we call evolvability. But again, you wouldn't be wrong if you say the design was adaptable, versatile. It's just the language we use. People use it confusingly when they talk about it. I prefer the term evolvable because it's got some distinguishing features. So a definition for evolvability, this comes from a well-known MIT professor, Olivier de Weck, which defines evolvability as follows. It's the extent to which a design can be inherited and changed across generations or over time. So there are a few words here we can highlight. So design is the first one. So note that design is the representation of the system. It's an abstract, so it's papers or computer models. It's not the actual manufactured system. So it means we're changing the design. It's not that we change the actual aircraft once it's been produced. Inherited, this means that there are traits that remains common across versions. So there are certain things we see over and over again. And if we look at this picture, you can see that they still look the same. They might be bigger or stretched, but there are things that are common. So inherit means that there are traits that continue far into the future. And with the Boeing 737, we still see traits that are essentially 60 years old, 80 years old. Changed means that something has changed. So something about the design has changed. And it's going to be inevitable. You're going to have to change something about the aeroplane eventually, usually, to remain competitive. And then generations, so usually this phenomenon occurs over very long periods of time. So that's the definition of evolvability. So there are a few obvious benefits. The first is that it's not a benefit, it's necessary. You're going to have to change your design whether you plan to or not. It's going to have to happen if you want to survive. How easy it is to change your design, that's going to depend whether you're going to survive as a company or not. It decreases risks if you have an evolvable design. It lowers development cost and time, but only for your derivatives, not for the initial one. It makes the manufacturer more nimble, so be able to respond more quickly to changes in the market. And the airlines also benefit from this commonality that you get, so the traits that are common. So often we can reduce training and things for derivatives. For example, we can reduce pilot training and so forth. But why is it difficult to design for evolvability? And there are many, many reasons. The first major one is uncertainty. And this is what we don't know. It's all about the future. The future is uncertain. We don't know where technology is going to go. We don't know how the socioeconomic environment is going to change. We don't know what the competitor is going to do. So we don't really know for what changes do we need to cater for. And a very big part of designing for evolvability is to try to think about what's the most likely outcomes and then trying to prepare for those changes. The second one is that we've talked a bit about over-design, so having extra margin or what we call excess in the design, so having a bigger wing, for example. This adds mass and drag, so unnecessarily, which affects the performance and which can affect the competitiveness of your aeroplane. And very much related to that, a larger aircraft is usually more expensive, or you could spend more money in trying to reduce the mass and things that you infuse to make your design more evolvable. So I'm going to do a little demonstration just to explain the thinking behind evolvability. So I've got a two-axis graph here. So we've got utility versus cost. Now, utility is something that measures how good the design is. So it combines a lot of factors usually. So you could put fuel burn in there and noise, for example, NOx emissions. You can combine all of these things. You can even include passenger comfort or a lot of different things you can put in there. So it measures how good your design is. Cost here could again be anything. It could be your development cost, or it could be the total life cycle cost. The only important thing is that you shouldn't double account. So you shouldn't put, for example, account for fuel burn, direct operating cost in the cost axis and include fuel burn in the utility. So you just need to be careful when you account for things. Now, a dot in this graph represents a single design. So this design has some utility and some cost. And you can think of this graph as a point in time or an era or a scenario. We can then have a future scenario, which we'll call epoch 2 in this case. So we've got epoch 1 and epoch 2. And remember, you can have many different scenarios in the future, so you can have multiple epoch 2s. Often when you design, your epoch 1 will be when the aircraft first enters into service, which could be 10 years from now, and then epoch 2 is beyond that. So you can have several scenarios for both epoch 1 and epoch 2. It's just important to keep that in mind. So you've designed your little aeroplane and it's got some utility and cost, but then when you go to the future, you could completely reuse that design, so you don't do any redesign or changes. Now, probably the utility will be lower because it would be less efficient than new designs and so forth. It wouldn't be as competitive. However, it'd be cheap to do it because there's no extra development time or cost, and the only cost would be the recurring cost, which would be your manufacturing cost. The other option is to design a new aeroplane, so completely new aircraft. This would have high utility, but also high cost because of the long development time and cost. The other option is then to take your aircraft and just make changes to it. So often you wouldn't quite be able to be as competitive as a brand new design, but there'll be less cost and time spent to develop it. Now, the idea with designing for evolvability is to design for change from the beginning, which will often come at a slight expense in utility and also more cost. So you could reuse that design as well, but what you would like to exploit now is that you've evolved that design at far lower cost. Now, in the early days of civil jet transport, the green design was often the case. It wasn't really planned or wasn't planned extensively enough, whereas nowadays evolvability is planned quite extensively, and my work is very much about helping that process, helping designers to do it faster. So I'm going to go quickly through a few examples of evolvability in aircraft. So I talked about the 367-80. This was an aircraft that Boeing built primarily for the purpose to test ideas for jet transport. And it eventually developed into the KC-135, which you also think of as a Boeing 707, but it's actually a different aircraft. And then the Boeing 787. Now, from the -80, the fuselage diameter increased for the KC-135 and again for the Boeing 707. Boeing didn't want to make this change, but in response to McDonnell Douglas, which introduced 6 abreast seating, they had to be competitive. The 707 also received extensive upgrades to its wing in very quick succession. So there were many variants, and it was a design that evolved very quickly and a lot. And eventually, some of the design features went on to the Boeing 707. So there are actually a top cross-section and a bottom cross-section when you look at the fuselage. And on the 727, the top section was reused, whereas the bottom section was made smaller. The 7027 eventually designs segments from that were used on the 737, which itself is going to be the next slide, which received extensive evolution. The 727, actually exactly the same fuselage cross-section, was also used on the Boeing 757. So here you can see a lineage from 1954 all the way to 1958. And many of these features from that original aircraft is still being used on new 737s today. This layout from the -80 is also the precursor for most modern jet transports. So you could see it as the progenitor for modern jet civil transport aircraft. So the Boeing 737 is an interesting example because it started off with low bypass turbofans. So you can see the engine there, the nacelle has got a very small diameter. When they wanted to, when new technology became available with the CFM56 engine, the high bypass ratio, or what we call medium bypass ratio, the larger fan diameter, there was a big problem with landing gear space. And changing the landing gear essentially means changing the wing. And changing the wing for an aircraft is essentially a redesign. It's a very significant design exercise to make changes to the wing. So with this next generation of 737, what's called now the Classic, the original was called the Original, and then we went to the Classic. What they had to do was put the engine further forward and upwards, and that actually was only made possible by the advent of computational fluid dynamics. An extensive studying to make that change happen without changing the landing gear. Then we went to the next generation, the 737NG. These received a larger wing, which was a root tip, and the chord was extended, which is a very difficult change again to implement. So it was a much broader redesign, but still extensive reuse of elements. The engine also had increased thrust ratings and further technology development, but the diameter remained pretty much the same. Then we went on to the MAX, which with the LEAP engine is again a bigger engine. So again, a big challenge in integrating that with the airframe. And actually for the longer versions of the MAX, there's a mechanism in the landing gear which allows you to still rotate. So it effectively increases your landing gear length during takeoff to allow you to rotate essentially. Probably the best example of an aircraft that was designed with evolvability very much in mind is the Airbus A300, so the original Airbus. So this aircraft was designed with excess volume, so you could increase the range significantly. Ample wing area and landing gear length. The landing gear length was so long that you could increase passenger capacity by 25% without changing anything about the landing gear. The airframe was also designed such that you could increase the maximum takeoff weight significantly with only minor structural changes. And in fact, the aircraft's range went from 1,200 nautical miles, I think, up to 4,400 nautical miles without any major changes to the wing, any major noticeable geometric changes to the wing. And the maximum takeoff weight went from, I think, 130 tons to almost 170 tons. So very, very amazingly evolvable aircraft. It changed into the another thing I should say is that many versions were studied from the outset. So even before the aircraft was introduced into service or manufactured, many derivatives were studied. One of these was the B10, or which later became the Airbus A310, which is actually a shortened version. Interesting thing about this aircraft is that the wing chord was reduced. They could use the same structural layout and many of the same structural characteristics, therefore, but the aerodynamics was completely new. And it also took some new understanding of transonic aerodynamics to make that possible. But it's the only example that I can find where a wing was shrunk like this. It's a very, very interesting example. These collectively changed into the Airbus A300-600, which was the last highest gross mass variant of the Airbus with a very long range. So completely different aircraft essentially from the original, but looking almost exactly the same. These designs were changed into the A340 and A330. The A340 eventually was changed. The design was upgraded to A340-600, which is an extended wing. So the wing chord was increased with like a wedge increase and a tip. And this is a very, very extensive redesign exercise, although it's not a redesign, it's not a new wing. So the decision was made that changing the existing wing is better than incurring the cost of a brand new wing, even though it might be less efficient than a new wing. And of course, the A330 eventually, Airbus had so much confidence in that design that it received new engines in the version of the A330 Neo, plus the changes to the wing. Arturo, I don't have the time displayed on my computer. I don't think we've got that much time left.
Yeah, about 15 minutes left.
Yes. This is a plot that showed how Boeing evolved its aircraft, and you can see here from the 757. Can I have that? Okay, the black lines show the 707, and you can see that many changes were made with the different versions. Later on, we see a pattern with the 737 for, if you look at the green lines and the pink lines. We call this pattern leap and branch. So you leap to a new, more efficient version, and then you branch out by increasing or decreasing essentially the fuselage length to get different payload versions. That would come at a cost of range. For the long-haul versions, Boeing started planning they got a very specific planning strategy that they do with their evolvability, which you can see clearly here with the 767. They introduce a version, then make it more efficient to extend the range, but keep the payload same, and then stretch it with the same new technologies. And then once they've got that, they try increase efficiency again to extend the range of the larger version. And this is done extensively with the 777 as well, which went up to the 300ER version. And they redesigned they extended that as far as they could, but eventually had to make major changes with the 777X, which has got a new wing design. Airbus follows a more typical leap and branch version. The A300 had you can see the extensive increase in range with not a big increase in payload. Now, how does this physically look? So if you want to increase payload, decrease range, these are images that I produced based on a survey of several aircraft and what the most common changes are. So obviously, as you would expect, you increase the fuselage length by adding plugs. Sometimes new engines, but not always. And sometimes with heavier versions, you fiddle a bit with the high lift devices. If you want to maintain payload and increase range, sometimes you're going to have to increase the wing area. That's for wing loading, but also to have more volume for fuel. And often extra fuel tanks are added in the fuselage to increase the range. Sometimes wingtip extensions and so forth you see as well. If you want to increase both payload and range, you're going to stretch and you're going to probably increase the wing, but not necessarily as we see could be achieved if you've designed with enough margin from the beginning. A more rare example is decreasing the payload, which we saw with the A310, and increasing range. This is often a more difficult change to do if you want to do it well, because you want to decrease the wing area essentially. And that's very expensive to do. So it's often a more difficult thing to do. You're also going to increase your, usually your stabilizers for stability purposes. So what are the lessons we can learn from these? It's important to have some sort of a strategy. So it's important to plan for evolvability. So either the leap or branch or Z or some other strategy. Leave margin in the volume, wing area, landing gear length and strength. This is very important, but it's very difficult to decide how much. The layout of the major components is important. So having engines under the wing allows you to more easily stretch the fuselage than having them at the back with the detail. There are several reasons for that. So the tube and wing plus podded engines under the wing is better. Structural strengthening is reasonably easy compared to big changes in geometry, especially with the wing. And smaller derivatives are usually more difficult to change. And there are also multiple ways of achieving a change. So you don't necessarily have to stretch the fuselage. You can internally change bulkhead spaces, but you have to have prepared for that change. Sometimes a clean sheet design is just better. So it's not necessarily that you should evolve an existing design. You should study also whether a new one is going to be better. Now, I quickly want to go through evolvability framework, and I think we're going to run out of time now. This is a process which I adapted from Michel Cardin, who was actually at the National University of Singapore for a while. He studied flexibility of engineering systems in general in quite a bit of detail. What you have is a baseline design. So you have to start with something. Then you account for uncertainty by doing scenario studies and so forth. You generate concepts for evolvability and do design space exploration. I'm going to go through these steps very briefly. So with the baseline design, you design essentially for your current requirements. And it's the normal process we learn in aircraft design. With uncertainty recognition, you want to capture and quantify the effects of the changing world on the system over time. So the questions you want to ask are, who are the stakeholders and how will their needs change? How will the changing world change requirements? What technologies will become available in the future and which ones should you prioritize? And what will the competition do? A common approach in aerospace is to do scenario planning. So you identify a few scenarios that you're going to get in the future. Once you get to the concept generation, there are two aspects of it: strategy generation and the actual enabler. So what's going to enable the changes to be made? Strategy is about who will make the change, would be the airframer or the airline could do it in service, but usually it's about changing the design. When will it be performed and in response to what changes? And then which enabler would be used. So common technique is what we call real options. This is a financial evaluation of each strategy. So just a simple example is you've got a baseline, then you can have all these options, either new, derivative, and will the derivative be planned or ad hoc? And you study all of these even before the aircraft is goes into service. I'm going to skip this one. It goes into quite a lot of detail. I want to go to some of the enablers. These are intuitive things, and this is what I would like to take you guys to take home. First of all, is to design as simple as you can. That means fewer components, minimize the number of interfaces between components, and minimize the number of secondary functions that each component does, and use already existing resources. So this just limits the number of components that can change. So it's a very simple thing. Try to keep your design as simple as possible. The second is what we call independence, and this is by ensuring that design parameters are as decoupled as possible, so that if you change one design parameter, it won't affect any other design parameters downstream. A related concept is modularity, and this is probably the most intuitive enabler. So this is where you cluster different components that have different functions into physical modules. And some extreme examples, like you can see, there is a removable cargo pod here on the left. and this concept for a modular military trainer where you can change the wings to change, and this is in service where you change between a low speed initial trainer and a high speed trainer. Scalability, this is the ability to scale. So the next enabler is very much related to this. So scalability is essentially, for example, to increase the fuselage length. And you need a few things to be able to do that. And that is what we call redundancy or excess or margin. So this is extra wing area, again, like we showed in the Boeing, the Airbus A300, and extra landing gear. So the image in the middle here is the DC-8, which is really long landing gear, and that enabled them to stretch the fuselage up to the one that we can see there on the right-hand side. Design space exploration is the computational side of things. So we've got millions of designs to study. So these concepts are simple, have excess, do modularity and things, but it becomes difficult when we've got many thousands of designs that we need to study. And this is really where my PhD came in. And I'll go briefly through an example of how it works. In my case, I look at pre-planned derivatives. So I look at what we call the near future. So this is when the aircraft will go into service the first time. So 10 years from now, for example, and then beyond that, so 20 years from now. And what I do is I design aircraft for both the near future and the far future. And then what I have to do is I need to find commonality between them. I could design ones now and then take for every baseline, do derivatives, but you can see that that's going to explode computationally. So I'd rather have a group of designs in the future and a small group of designs in the near future, and then find commonality. So essentially work backwards. And to do that, you need some sort of a way to predict commonality. So I developed a method which is a type of artificial intelligence that's used in DNA sequencing and so forth to catch common features across things. This is going to be a whole lecture in itself, so I'm not going to go into detail, but essentially it allows you to identify commonality between airframes. So what it allows you to do is, so for example, in the near future, I can select a design, the blue design, and then I can see how the far future designs cost will reduce based on commonality. So you can see some reduce more than others and some less. I can choose another design and see that the designs change in the far future. Another way is to select a design and then see what the level of commonality is. Another design, or you can select one in the far future, see what's the commonality in the near future, and so forth. So this allows you to explore. Another technique I was developing was a filtering technique for reducing the number of options. So this was just a technique that looks at different criteria and commonality to reduce the number of the future options. Question time again, but I think we're running out of time. So all I want to end off with is that we are essentially where we were in the early 50s, late 40s. We're at the dawn of a new era with new propulsion, new technologies. Essentially, we have it slightly more difficult than the designers from those time had, because they knew that the jet engine is coming. We don't know exactly what propulsion technologies will be the best. So we've got a few there, and more electric propulsion, ultra-high bypass turbofans, geared open rotors. In a sense, you can design for these, leaving margin, for example. You just don't want to overdo it. Electrical propulsion might enable changeability because if you've got multiple propulsors, you can work a lot with scalability and modularity. So there's an opportunity there. With fuels, we're probably going to have to design aircraft that can evolve to different fuels. So for example, from sustainable aviation fuels to hydrogen. Concepts is a difficult one. As I explained, the tube and wing, there's a reason why it's so common, because it works. It works really well. So designing new concepts to be more aerodynamically efficient is a challenge. It's going to require some study to see how we could evolve these further into the future. And all of these have to be kept in mind with what regulations are doing, what's happening in politics, the economy, competition, shown there by the little fish catching the other fish. So there'll be new competitors. We want to know what the competition is going to do. And then the design process. So big challenges in enabling us to study all these things, study changeability. And this is really where my work comes in on the computational side to allow us to study this in detail. So a well-designed aircraft is evolvable. It's got many benefits like decreasing risk and lowering cost and time. It's difficult to design for because the future is uncertain. Therefore, study the future, follow a strategy, and incorporate the changeability enablers and compute. And I'm going to leave you with this quote from Darwin. It's not the strongest of the species that survives, nor the most intelligent. It's the one that's most adaptable to change. And I think with aircraft, it's the same.
Thank you, Esteban, or Dr. Esteban. Thanks for the presentation of your lecture. Please now we open the session to questions and answers. Yes, we apologize. We are running out of time, but we'll allow about 10 more minutes or even more. I think Esteban wanted to present, gave also an introduction of what is evolvability for the benefit of the students. So it took a little bit more time, but yeah, it's very interesting. So yes, we have a question. I can see Ian Taylor is raised his hand. Please, you're on mute. Yeah.
Yeah, hopefully you can hear me.
Yeah, very well.
Okay, well, thanks very much for the presentation, and thanks very much on behalf of SIT and Glasgow for agreeing to do this. It's very interesting. It's very interesting. I'm glad you mentioned engines as well in the mix, because that's my background, and it's definitely a similar theme. But my question is, one thing you didn't mention, which I think is a limiting factor, and reflecting on what you said at the end there with new technologies, is the infrastructure of airports.
Yeah,
that's been the limitation on the high bypass engines, the open rotors, and for new configurations that deviate from the sort of tube and wing. How will that fit with the airport infrastructure, and how does that fit into the cost and the evolvability?
Yes, it's a major part of what contributes to the uncertainty. The other problem is that it could happen in some airports but not others. So in some regions in the world, for example, we could introduce hydrogen, this is an extreme example, faster than at other places. So you would have an aircraft, you would need to have an aircraft that would be versatile for both those cases. And that's part of the challenge in how do you enable that, and whether it's reasonable to do that. That's the big question. All these, for example, with the open rotor is also the extensive noise, but there are promises that the noise could be reduced. So the question is, how much do we rely on that promise? It might not materialize, and then we have an aircraft that's probably designed for that. And that's part of the risk.
I mean, one other thing I was thinking is the way airports are structured. There's a fixed amount of distance between each gate, and each gate comes across at a set height.
Yes,
and that imposes some quite strict design limitations on all the aircraft.
Yes, yeah, absolutely. It is a constraint, and either airports will have to evolve simultaneously. Yeah. The whole infrastructure, it's not just the airports. infrastructure in general, if we're going to go to sustainable aviation fuels, hydrogen, that will have to evolve simultaneously. And I think a particular challenge, which I may not have articulated well enough, is to handle this transition. So having aircraft that, again, can exploit some of that, but can still operate as normal when you don't have that benefits in different regions of the world.
Okay, thanks. I mean, yeah, that's very relevant because it is very relevant to the project the students are currently working on as part of this activity. With they're looking at new powertrains and moving away from carbon, and infrastructure has been one of their challenges. So yeah, thanks very much. That was interesting. Thank you.
Yeah,
I won't hog the floor. I'll pass on to someone else.
Thank you, Ian. So now Henrik is raising his hand for a question. Please,
okay,
Henrik.
I will only ask a question if we get one from the students before. I don't want to.
Yeah, I would love to hear from the students.
Yes.
But I want to say thank you to Arturo and Devon for the webinar. It's very interesting. I have one question. Okay. The elephant in the room, right, is COVID. Okay, so you talked about predicting events and so on and so on. So okay, I guess nobody could predict COVID. Commercial aviation was dead last year. From your point of view and your expertise, and it's interesting for the students, right? How will manufacturers account for such extreme events in their future designs? And how would aircraft evolve with that?
Yeah, I deliberately avoided it.
Sorry.
Because it's such an extreme event, right? That there's a limit to what I think you can prepare for, and I think to some extent it's not the aircraft itself, but it would be the wider supply chain and business model that you would need to think about for cases like these. If you go to, for example, if a part of your business model is you're a manufacturer of some component or components or subsystems, and your part of your business model is that you do the servicing and maintenance on that, you're going to be hit quite badly by something like the pandemic. I think there's a limit to what you can do in the airplane itself. I think the big thing will probably be capacity. And capacity is so passenger numbers. I think that's one of the easiest things to cater for if you've got a tube and wing, because you stretch it or you shrink it, and that's something I think the airframers are very well versed in designing for. So from the aircraft itself, it's probably capacity. The rest is really how your whole supply chain will be affected and so forth, and your business model, as I said. These are really the considerations. So if you're really betting on one supplier and they go bust during a summer, then obviously that will be a major issue. So I've limited the discussion here to the airframe itself mostly. I've talked a bit about the engine, but there are a whole host of other systems surrounding it. We've talked about the infrastructure, but there's also the air transport system itself, the largest system, the infrastructure. All these are related, and from the manufacturing side, it's your whole supply chain, your company organization and things, which is very tightly linked with this. And there's a big study, a big area of research in how to account for all of these factors when you're doing this. But it's a very, very difficult problem just because of the sheer number of factors that you have to consider and the uncertainty, which is a killer. And yeah, so I think as an aircraft designer, you got to scope. And something as severe as COVID is is for the guys at the top, the business people that think about the business side of things. It's not that it's not related, but yeah, we have to focus on what we can focus.
Yeah, thanks, and sorry for asking that question linked to
COVID.
No, it's relevant because Singapore is very big, focusing on MRO business. So I mean, that's what you said, right? And that's basically down the line, right? If we don't have any aircraft flying, then they don't need to be maintained. So that's a big factor.
Yeah,
Thanks.
yeah.
Okay. Thank you.
Any other questions? Anyone would like to? Not only the students, so we have other guests or people who joined from the UK. No questions?
I don't bite.
Comments as well. Yes, welcome.
Okay. Some participants, right? No, nothing.
Yes.
Hi,
yes,
sir. Good to see you.
Good to see you again.
Yeah.
You're with Conqueror from the Royal Thai Air Force Academy.
Thank you.
We met in UK for a while. Back to the questions. It's always kind of bothering me or like it entrenched me on the word of commonality or adaptability for the families of aircraft since the dawn of the aviation. Every once in a while people came up across these concepts.
Yes.
From time to time.
Mm-hmm.
And most of them kind of okay. But it is not exactly. I would boldly claim that up to this point, we haven't seen any case that we can proudly say that it works. Yep, that's just a bit. So my question is, are our technology at this point of time can justify to embrace the concept of the commonality for the sustainable application in aviation?
Are you saying that, for example, that we to incorporate new concepts such as, for example, hydrogen propulsion, we need to essentially rethink the whole thing, and we need a yes. This is something that I'm thinking quite a bit about. There are two things we can try and do. We can try to think how we can evolve current concepts to those, and that will come with constraints. That's the thing about evolvability. It will come with constraints. Or we can design a new concept, incorporating some new technology for, to match that perfectly. The point is that you even if you do that, you're going to have to make sure that that's evolvable beyond. So if you have a say blended wing body, and we're going to do that with hydrogen, for example, you're going to have to ensure that that's going to be evolvable, so that design is going to be evolvable. So I'm not dictating which way we should go. I think this is my own personal opinion, but designing and building a new concept, I'm not sure whether the airframers are going to take the risk. I probably think it's going to be evolved from what we see today. It's with the Boeing was in a very good position when they introduced the 367-80. That aircraft was designed to play around and see what we can do. It was developed very quickly, built in 2 years. We can't do that anymore. And just for a normal looking aeroplane that the average person wouldn't be able to tell the difference. An aeroplane now takes 11, 12 years to develop. So once you're going to try something new, I just don't see that the risk doesn't add up to me. I don't think we're going to see that, even though that's what should happen. And hopefully this is where we, as the industry, may get support from government or somewhere else to support this process, where we could, for example, have a demonstrator where we could iron out the issues. But I don't see one of the big airframers taking on that risk alone. Yeah. So it's a very difficult thing. We're not, when we look at the early days of the jet age, we got many different types of configurations, different ways, different ideas of doing. But the reason I had the -80 is because it's the example that we see today. It's the one that survived, and there's a reason for that. That configuration is just very evolvable. But it's evolvable for the jet engine kerosene. It may not be for what we're facing. And this is the particular challenge that we face at the moment.
Thank you.
Sorry, that was a very long-winded answer, but yeah.
Glad I'd ask.
Thank you, Steven, and thank you, Atom, for the question. And it's good to see you. Yes, Atom, Steven, and I shared some time together in Cranfield. It's nice to see you here. Yes, okay. We are, I guess, already over time. I'm just going to, again, thank the speaker, Steven. And also, I want to invite the audience to, if you haven't joined us in the Royal Aeronautical Society Singapore branch, we have some groups, Facebook, LinkedIn, so please join us there. But we're going to organize more events in the next months, coming months, and so please keep in touch. And but once again, coming back to our speaker of today webinar, thank you very much, Steven, and thank you.
Thanks for inviting me.
Yes, thank you. And also thank you for the students and everybody who joined. It's always good to have a good audience. I know the students probably trying to finish their projects, and so we leave you to that, to finish. And we're obviously going to see very good projects after this lecture.
Yeah, it should all be evolvable.
They should be evolvable.
Say simple evolvability, yeah. And I have to survive the future.
That's given me some good questions for Friday afternoon.
Excellent.
Thank you very much. Really enjoyed it.
Yes. Okay. So we'll close this session and see you until next time, next event from the Royal Aeronautical Society Singapore, SIT, and University of Glasgow. Thank you.
Thanks.